So welcome back to the second part. To make it short, I was jumping from the question of cyclic convolution. I'm going to right away to Gabor expansions or so. So I was explaining in the meantime a little bit that cyclic convolution can be viewed as, well, everything that happens on periodic functions can be represented by functions on the fundamental domain. But these functions on the fundamental domain, if you're wrapping them up, can be viewed as functions on the torus. And the torus would be a copy of the real line modulo your invariant subgroup. So it would be RD modulo lambda, or in the simple case of a Shah distribution on the integers, it would be the real line modulo integers, which is known to be the torus, or can be identified with the unit circle of the complex plane, which is exactly the image of the real line under the exponential mapping t goes to e to the 2 pi I t. So I call it the wrap-up function. You take a rope, you wrap it around the unit circle, and each time you have the multiple of 2 pi, you're back to 1, which is the 0 element, or the neutral element of the multiplicative group of complex numbers of absolute value 1, and you're wrapping up. And because this homomorphism t goes to e to the 2 pi I t is having exactly the integers as the set of all the points in the real line where you go through the identity element. You can identify R modulo Z. Now, the idea of using the zero setting is quite useful because in the literature on the classical setting, you find many conditions, for example, validity of Poisson's formula, which from a modern viewpoint can be seen as sufficient conditions for functions to belong to a zero. And for a zero, we have seen that the Poisson formula is valid. But we have also seen that it can be used by taking this generalized Fourier transform to show that the Dirac comp goes to the Dirac comp, and then we can stretch the Dirac comp. You get the ST row operator changes the lattice constant. The D row operator is also doing it, but with a correction of amplitudes. So this is really the world where we will continue to work, and we would like to understand it better and what the significance is for Gabor analysis, time frequency analysis. So whereas standard introductions to a zero nowadays, for example, in the book of Gröchenig, are starting from L2 and define a zero as a subspace, we have done another path. We have taken the path of first starting with bounded measures, then introducing Fourier algebra, then introducing a zero, kind of doing by hand, following the quasi-historical path, doing a construction of a space called a zero, and take the dual space, and inside the dual space we do everything we want to do. And I think we can do actually almost all the things that we can expect. So for example, I was trying to show you an intuitive approach to the Gabor expansion of signals. And in a way, we were using a variant which is of the Shannon sampling theorem. Recall, Shannon sampling theorem says, if you give me a band-limited function, and we've seen the pictures, which has a compactly supported Fourier transform, and you sample the function, it's like multiplying with Dirac comp, which means periodizing the Fourier transform. But if you have a periodization which is coarse enough, keyword is a Nyquist rate, then you can recover, or you can say it's the same thing to know the function in a periodic version or in a local version only. So that's exactly the same information. Now, what we do here when we try to do the naive Gabor expansion is to say, well, every function in a zero, and that's the setting where usually things work completely stable and controllable, can be cut into pieces. So what you see is cutting a function with the help of a partition of unity, a BUPU, into pieces. So if we want to understand what the Gabor expansion of a function is, we can cut it into pieces, and it's clear that each piece has a label saying, well, we are near the lattice point number 5 or 12 or so, and things are going on. So I just took a very simple complex valued function. You see real part, imaginary part, everything localized or so. And then the idea was to say, I'm not sure if I can show you the picture. Yeah, to say, well, if I would periodize this function, then I could take the information in the periodic version as the same information as the local version. But I have to be able to come back from the periodized version to the original version. So you have original version periodized, convolution with the Dirac comp is giving the periodic version. If it's well enough separated, periodic version multiplied with the function tau is giving you such a function here. And so the proof that I was writing in the notes, or we had already a discussion on this, was essentially the idea that if you give me any function which, after blowing it up in the microscope, so to say, has some small plateau, so that all our pieces are fitting inside, as in my example here, then I could use it as a building block. I would say, well, you give me this basic periodic function. I can expand it into a Fourier series, which means I take this fundamental domain, we take the classical Fourier coefficients, and we produce a trigonometric polynomial, I mean, an absolutely convergent Fourier series expansion, which is representing the periodic function. And that periodic function can be multiplied with this, and then we are getting for free Gabor expansion. So I hope I have it here. No, that's now a difficulty. Yeah, here I'm saying what I'm getting. So we take these pieces and we use, we write this version in this Gabor expansion the following way. I see. Yeah, so in the previous part, I was showing, maybe I just go through this, sorry. So the first proof was essentially saying I can fabricate an expansion by taking a BUPU for the analysis. So that was saying essentially, instead of taking Fourier coefficients of f multiplied with phi, and phi localized at lattice point number k, we are writing it as a scalar product. So we already want to have a full organization. We take all the frequencies with some lattice constant b in the frequency domain, and all the building blocks, and the Gabor system is the collection of all these time frequency shifted versions. So in my MATLAB experiment, I was creating a Gauss function, and a discrete Gauss function. I was having a single space of dimension 480, and I was producing along a lattice 720 of these elements. And now the main question is, whereas it's kind of naive and derived almost like Shannon sampling theorem, that if you do a fine partition of unity and you use big plateau functions tau for synthesis, then you can get such an expansion. Now, of course, it's easier if your periodization is very big, and we know that how do you get big periods? If it means that you have a fine frequency resolution, so your B has to be smaller than 1. Now, if you play around with this construction or so, I would say if you're careful doing it, then I think you would be able to find out that for A times B larger than 1, that's kind of near the Nyquist rate in a way, you can find functions where you can get such an expansion already. But the question of Gabor analysis is in a way more intricate, in the sense that we are asking the following question. Is it true that, I mean, Gabor himself, maybe I should say this, was saying that every function can be represented in such a way, and he was suggesting to use a equals b equals 1, so to use the integer frequency shifts and time shifts, and to take the Gauss function. Now, why did he make this argument? Because, or what was the intuition behind it? First of all, if you're choosing a and b small, so for example, if I would take a equals b equals, I don't know, 1 quarter, let's say, then if somebody shows me, and that's a true statement, that I could do it already with a equals b 1/2 quite easily, then you would say, well, if I can do it with 1/2, I take maybe just if you take a quarter, you can use only every second one from 1/2, but you can also shift it. So you have, the problem is if a and b are small, you don't only get a huge number of Gabor coefficients, so in linear algebra sense, you would have too many storage, but you would also have more and more linear dependency. So what is the idea? If your family of vectors in your Hilbert space is too big, you thin it out or so. Now, the bad story with this Gabor system is they are such that they are dense. The linear combinations are dense in the Gabor case, but they are not spanning. That means we can approximate better and better, but the coefficients that we need, so if you say I'm allowing arbitrary coefficients, they would blow up and there is no limit relationship. And so the S0 setting is much better. And here you get, if you start with S0, then of course you get an absolutely convergent Fourier series for each piece. So this sum of the L1 pieces is depending only on the position and can be controlled by the Fourier algebra norm of f localized to T alpha kf. And then you sum up over all the positions, and that's again summable by the construction of the Siegel algebra. Okay, so we have a statement that says we can expect, and to some extent we can really do it, that every S0 function can be expanded in such a way with L1 coefficients, and these L1 coefficients are obtained in a very naive way, as if this whole thing was an orthonormal system. Now, recall that you have orthonormal systems in arbitrary spaces with a scalar product, so in Hilbert spaces, and that you have the same theorem. And there is a term of completeness which is different from completeness in the setting of Banach spaces. So there's a theorem that people learn in the course on functional analysis. An orthonormal system is complete if and only if you have such a representation or so, but with constant 1 actually. But this assumes that you have orthogonality. Here we are saying that you're just expanding a vector in the Hilbert space in a way as if it was an orthonormal expansion. And a good way that you could have is to say, well, you would like to take any system which is an orthonormal system in a larger Hilbert space, and then you project it back. So maybe I'm showing myself. Yeah. No, that's wrong. Sorry. Yeah, maybe I don't do it now. I wanted to essentially say that if you would take an orthonormal basis and you project it in the right way, you have in R3, you project it onto a plane, then you would see triangle, I mean the Mercedes star, so to say. And these are 3 vectors which behave exactly like an orthonormal system with respect to expanding every coefficient, every vector in the plane, and it's a frame of redundancy 3/2 or so. Now, I want to come back, and hopefully you're seeing now my standard picture of a Banach-Gelfand triple to the situation of Gabor expansion for the Banach-Gelfand triple. That's kind of more or less also where the usefulness of S0 appeared after many years of, well, just having a funny example of a Siegel algebra. And it's because at the moment my statement was that if you're careful, then you can get L1 coefficients from the S0 elements. But you can also take the L2 coefficients for L2 functions, and you can get bounded coefficients for S0 prime distributions. So I will try to help you to understand how Gabor analysis is allowed to describe the different building blocks by ordinary sequence spaces. So again, I hope I can go to that other slide. Yeah. So from a talk which I gave recently, I'm jumping into the definition of a Banach-Gelfand triple or a rigid Hilbert spaces. So it's a Hilbert space with decoration or so. The abstract situation is that somebody is having a Banach space sitting inside a Hilbert space here, L2, and that's embedded into S0 prime. It's the dual of the small guy. So what is important, also used in an abstract setting, that S0 stands in L2, so we can approximate elements from L2 here. We more or less took, this is the definition, we took Cauchy sequences in respect to the L2 norm, but which are, and we're showing that they are elements of S0 prime, which can be reached in the weak star limit, but with Cauchy condition in the L2 spirit. Now, in our case, we view S0 as a space of test function. This is the Hilbert space, and we call the dual space of mild distributions. And we have this weak star density. And weak star convergence, of course, means this here. Actually, it should be S0 here. And as so often I'm telling you, please think of rational and real numbers. And because in this talk I tried to convey the analogy in a little bit further way, I'm saying, well, we are used to invert in the rationals in this way. We're used to do this, but in reality, this is as abstract as applying the inverse Fourier transform, the inverse extended Fourier transform to distributions. So what does it mean to have this formula in line number 4? Integral from minus infinity or so. Mathematicians are saying, oh, it's not a convergence, so what can they do? Well, somehow it would be reasonable to think that the integral for s equals 0 is plus infinity because you're integrating constant 1. But if you replace it by 3 times, you would also get plus infinity. So what is the difference between delta and 3 delta 0? So kind of the point is, this is just a symbol, like take the inverse Fourier transform of constant 1. And of course, that's well defined in the calculations that we have here. We also are used to compute with these numbers and concatenate these objects in a good way. And we will see that this is something that we will do also with operators. So general operators will be represented by kind of continuous matrices. This will be the so-called kernel theorem, and we will do this. So, but okay, so maybe following that slide, I'm just telling you that standard approach to S0 would be, we start with time shift, frequency shift, time frequency shifts, and we define the short-term Fourier transform. Standard picture is my Beethoven image, very long. Display for a melody like da 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 on the piano, and we had already our characterization. So for us, it was a characterization derived from the continuous equivalent norm that you can characterize it by the integrability of the short-time Fourier transform. And we were having the obvious properties that time frequency shifts, time shift by u followed by frequency shift of eta is isometric, And rotation by 90 degrees, if we use the Gauss window, is giving us an isometric invariance under the Fourier transform. In the old days, before I was using this characterization, people were asking me, well, is the Fourier transform isometric on a zero? And I was always saying, no, you cannot talk about this because the norm is given by BUPU, and every new BUPU will give you a new norm, and therefore you can only say it's a bounded and boundedly invertible mapping. But now I would say take for our concrete setting a Gauss function, and then you have isometric statement. Now all this is captured and in the abstract setting, and I want to introduce it a little bit at least. If somebody is giving you two such triples, always a small Banach space with a dual space which is allowing to embed it, and this is really the situation which has started, I don't know, maybe with L1 intersected the Fourier algebra. That's already small enough to be embedded into the dual space, but that wouldn't be used. We could take the Wiener algebra, which is embedded into the space of translation bounded measures. That's already nice, but it's not Fourier invariant. And it's, of course, much better to take the space, the zero space, and then you have this dual space. But people in partial differential equations may know about Sobolev spaces. Sobolev spaces are more or less inverse Fourier transform of weighted L2 spaces. So you would say, if you give me a Sobolev space, it's inside L2, and the dual space is a bigger space. So actually, the standard setting for differential equation, if you have a Laplace operator, you would say, I start with a Sobolev space of order +1, the dual space is the Sobolev space of -1, and in between you have the Hilbert space L2. So in a way, Sobolev spaces, triple of Sobolev spaces, is a Banach-Gelfand triple in my sense. It would be even a Hilbert-Gelfand triple, but I'm not using it. For me, the important thing is you don't have to use something like a Schwartz space with a complicated topology. Even a Banach space can be extremely useful. Now, if you have two such objects, and the prototype, as we will see all the time, is sequence space, little L1, little L2, little L infinity, bounded sequences. The prototype of such a mapping would be that you have a mapping which preserves the structure. So it maps the small space into the small space. It is maybe even unitary at the Hilbert space level, and it extends in a unique weak star to weak star way to this here. So sometimes you can say, well, I'm proving something like a zero goes to a zero. Then I extend it by duality, and I'm getting the extended Fourier transform. It's really an extension, and that's important. And then I'm deriving from this the Plancherel theorem. We did it a slightly different, half traditional way. We are saying L2 goes to L2 is the Plancherel theorem, which I proved beforehand after defining L2. And restricting the Plancherel transform to a zero, of course, or to L1 intersected Fourier algebra, which is in between, gives me this one, but then we have extended it later on. But altogether, we can say that the Fourier transform is a Banach-Gelfand triple isomorphism, and because you have the same spaces before and afterwards, it's an automorphism even, yeah. Okay, now when I'm giving talks on this object or this category of Banach-Gelfand triples, I usually say that everybody knows that every Hilbert space is isomorphic. Every separable Hilbert space is isomorphic to the sequence of square integrable functions. So essentially, if you're giving me any finite dimensional vector space, you can identify it with the coefficients with respect to a basis, and then you can say, well, I take the Euclidean norm on the sequence of coefficients. But now you let n go to infinity. You have a countable index set. Typically, people take the natural numbers and they say, well, the square summable sequences called little L2 is now the space of all infinite countably indexed vectors which have a finite Euclidean length. So this is the prototype of a separable Hilbert space. And Fourier series expansions, so we are here on the torus, say that we can expand every L2 function on the unit interval or on the torus into a sequence, and it's the Plancherel theorem appearing here as Parseval equality, which appears in the classical setting, say, well, the L2 norm in the norm in the Hilbert space of a function here is exactly the coefficient norm here, also in the Euclidean sense. Now, it was again Wiener who was saying, well, sometimes these convergence issues are too delicate. Let's just take inside of L2 on the torus the absolutely convergent Fourier series. Now, these absolutely convergent Fourier series are exactly those which correspond to L1. So somehow, starting from L2, you're saying L1 is inside L2. But what are the functions in L2 which correspond to L1? And so you take A. Now, once you have A, it's a Banach space, and of course you take the L1 norm of this space, and you're saying, well, but maybe we should look at the dual space. It's an infinite dimensional Banach space, so let's look at the linear functionals on A of t. And that's what people call pseudo-measures. Then distribution theory came in, and in the setting of tempered distributions, but also in our setting, we could really just take, you fix a lattice, you take the absolutely convergent Fourier series, and you find out that the linear functionals on this space can be identified with sequences which are exactly the generalized Fourier coefficients, and they are in L infinity. So, I mean, what is a pseudo measure? Well, you're taking finite sections of a bounded sequences. Finite sections are in L1, so they are inside of A, but they don't converge in the sense of A, but only when you act them on some A. So that's exactly the weak star convergence. So what I'm saying is the classical terminology of the algebra of absolutely convergent Fourier series inside the periodic L2 functions, which has the dual space of pseudo measures, they are a triple exactly in the spirit of my abstract concept. And the Fourier transform now, the classical Fourier transform at the level of L2 or restricted to A of t going to L1 is an isomorphism in the sense of Banach-Gelfand triple. So it's not anything magic. So maybe as a summary, and I should probably jump to Gabor analysis only later. Summary of what I can say about the Fourier transform is it is it's a Banach-Gelfand triple automorphism. It's even a unitary Banach-Gelfand triple automorphism. So recall, mapping between two Hilbert spaces is called unitary if it's a bijection and if it preserves the scalar product, hence if it preserves the norms. So you can also say, due to the polarization identity, if you have a bijective mapping from one Hilbert space to another one, here it's more or less the same. It's L2 on the time side, and it's L2 on the frequency side. You can say it's maybe in image processing, D equals 2, you have square summable pixel images, and you have wave number domain or so, but let's say in the continuous non-periodic case, this is the same space. And it restricts to a zero. Rather, I would say it is well defined on a zero. The Fourier inversion theorem is working fine, but it is isometric. So we were actually proving the Plancherel theorem by first proving this in a slightly larger domain. We were saying if we do it on the Wiener algebra and the Fourier transform is in the Wiener algebra, and that's a space containing this slightly bigger, you can prove it with Riemann integrals that you have this fundamental relationship which implies the Fourier inversion theorem, which implies Plancherel. So starting from this one, inversion, now Fourier inversion is easy here, gives you some statement like this, but it's not an integral transform anymore. The Fourier transform of a sinc function in the spirit of L2 is the limit of the Fourier transform of the truncated things, or you multiply your L2 function sinc as an example, or with some decaying blue curve as we had it at the beginning, That's a Gauss function, which is very flat. Then you take the Fourier transform, and then you take the limit, and it is convergent. But it's also important that this can be extended to a weak star to weak star convergent thing, and that's the extended Fourier transform that we have. Now, again, why is the weak star convergence so important? It's important because we have the property that S0 is weak star dense in S0 prime. So if you say, I want to extend the Fourier transform from the ordinary integral transform for harmless and decent functions to something bigger, I have to do it in this way, I will get the same thing. On the other hand, we have seen that even the periodic discrete measures are embedded into S0 prime. They are finite linear combinations of Dirac combs. Dirac combs are mild distributions, finite linear combinations are again. And we have shown that if you give me the coefficients and the description of these Dirac combs in an appropriate way, I can compute with the help of the FFT or the DFT what the Fourier transform is. So what if you approximate now a general element, could be even a nice function by discrete continuous functions, and you compute the Fourier transform with the help of discrete Fourier transforms? And the answer is then you would get the continuous Fourier transform. Of course, you can do the same thing with periodic functions. That's why I wanted to discuss a little bit more, but I was not doing it properly today. The question of how can you expand the functions which are periodic and let the period go to infinity. That would be the way to explain why the Fourier transform takes the shape it takes. And I observe quite often in the books, in the engineering books, that people are deriving in a heuristic way the formula for the Fourier transform. That's fine. And they also take the inverse Fourier transform, which is, of course, going back from the Fourier coefficients, which are obtained by Fourier analysis, back to the signal, which is Fourier synthesis. And then they write, okay, it's clear that the inverse Fourier transform must be the expected integral formula or so. But the danger in such an explanation is that you're using the name inverse Fourier transform already before showing that it's actually the inverse of the forward Fourier transform. So that's quite different in our setting. We were saying, well, we define the forward Fourier transform in a decent way. We take limits in the right way, and then we get a mapping which is weak star continuous, also norm to norm continuous on the dual space. And we would like to know what the inverse Fourier transform is. And it's really very easy then to show that it's the same formula. So either you extend the ordinary inverse Fourier transform, that's what people do heuristically, or you're saying, well, the inverse Fourier transform of sigma hat applied to a test function f is the same as sigma applied to the inverse Fourier transform of the test function, which is kind of easy. So I find it a very important thing. And also the fact that you could say, well, the Fourier transform is mapping pure frequencies into characters and characters into pure frequency, or you say Fourier transform should be the thing that gives me the coefficients of a trigonometric polynomial if I insert a trigonometric polynomial, whether the frequencies are sitting on a lattice or no. It's all these kind of, so there is no other way of doing it. Now, last statement for today, I would like to mention at least that what is this strange weak star convergence? So we have seen a number of examples at the beginning of this session of objects which are weak star convergent with some limit or so. But I'm giving you first a necessary statement and I claim a converse. So if you're saying I have a sequence sigma n, so maybe I go, no, just, it's sequence sigma n, and I prefer to take a bounded sequence of functionals. So a bounded sequence of mild distributions is weak star convergent, means whenever you apply it to a test function, you observe it's going to sigma 0 of f. Well, actually, I mention once more that if it just converges for every possible test function, the limit will automatically be a linear functional, and even better, by the Banach-Steinhaus theorem, will be a bounded linear functional. So boundedness of the sequence sigma n is kind of automatic once you're having weak star convergence in the strict sense. But I prefer to assume to do it in a slightly different way, to assume boundedness first and then assume convergence only on a dense subspace. That's practically much better. So you test only, for example, on band-limited L1 functions, you're tested only on compactly supported elements of S0 or such a thing. Okay, good. Now, a necessary consequence is that this short-time Fourier transform, and of course this is just sigma n applied to a time frequency shifted version of your test function, should go to the same value of the sigma. So you have pointwise convergence, but that's a good, easy exercise. If you have pointwise convergence, you have uniform convergence on finite sets, and then you get even uniform convergence over bounded sets. So it's the very simple idea that norm convergence in S0 prime, norm of S0 prime, we will see, is just the maximum norm on the short time Fourier transform domain. So if you have uniform convergence of Vg sigma n to Vg sigma 0, you have norm convergence. Now you have pointwise, but actually practically more interesting, uniform convergence over compact sets. So, it's exactly like the pure frequencies. If you take pure frequencies going to 0, that means that the function is going to constant 1 more and more of a larger, better and better over larger and larger domains. So now we have the same effect, but on the spectrogram level. So again, it tells you through the spectrogram, you can understand much better what happens. So my standard joke is, if you're buying a CD, somebody has recorded the spectrogram, actually a sample spectrogram that's close to Gabor expansion, up to frequency 20 kilohertz, actually even more, but that's what is stored on the CD, even a little bit quantized, and only for those 3 minutes. But you don't care. Your piece of music should be reproduced almost perfectly in the area of interest, which is your 3-minute interval of time for the piece of music, and the frequency range from 0 to 20 kilohertz. And thanks to Shannon, we have all the information that we can hear with our auditory system, because no human being can hear anything beyond 20 kilohertz. Actually, you're lucky if you're still here more than 12 kilohertz, which probably I will not do anymore. Okay, so in this way, I have tried to reconnect a little bit the approach that we have taken and the modes of convergence with the time frequency business. And it's time to stop for today, and I will continue with some more practical demonstrations next Thursday. Thank you very much.